guys, my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we're going to talk about the Nernst equation, which is a very important equation when talking about electrochemistry. But before we do that, let's talk about how concentration affects the cell potential. And this will lead into what we want to talk about in terms of this equation. So let's look at an example. We have 2 aluminum, which is a solid, plus 3 Mn2+, which is aqueous, going to 2 aluminum 3+, plus 3 Mn. And for this reaction, the cell potential, and since there's a 0 here, it means that it's at standard conditions, is 0.48 volts. So now, let's use Le Chatelier's principle, which we learned before, right? Where we can look at different relationships between reactants and products. So let's say we increase the concentration of Mn2+ to be greater than 1 molar. What does this mean? This means that E cell is going to be greater than the value given right here under standard conditions, because now we're increasing the reactants. On the other hand, if we increase the concentration of aluminum 3+ to be greater than 1 molar, and again, we're using the concentration of 1 molar because this says this is under standard conditions, which is at a concentration of 1 molar. So if we're now increasing the concentration of the products, now E cell is going to be less than the potential at standard conditions. So as you can see, by using Le Chatelier's principle, depending on whether you increase the reactants or the products, that cell potential is going to differ from the standard condition cell potential. So from here, to quantitatively determine the direction of electron transfer under non-standard conditions, we have to use the Nernst equation. So basically, direction of electron transfer under non-standard conditions. So let me derive this equation for you. So the dependence of cell potential on concentration can be derived from these 2 equations that we already know. The change in the free energy, let me make this an arrow so it doesn't look like a minus sign, is delta G naught plus RT ln Q. But instead of Q or K, which is the equilibrium quotient or the equilibrium constant, let's write it out as the concentration of the products over the concentration of the reactants. And you should have already seen this equation from thermodynamics. We also just saw the equation delta G is negative NFE, right? This was relating the free energy change to the number of moles, Faraday's constant, and the cell potential. So now we can equate these 2 to one another, right? Because they both equal delta G. And we can end up with negative NFE equals delta G naught plus RT ln product over reactants. From here, let's solve for the cell potential. And when we do so, we end up with E being equal to negative delta G naught over NF minus RT over NF, natural log of products over reactants. And then from here, remember that this part, negative delta G naught over NF, is equal to the cell potential at standard conditions, right? So we can write this out as E equals cell potential at standard conditions minus RT over NF, natural log of products over reactants. And so this is the Nernst equation, which is more often seen as E equals E naught minus RT over NF Q. Remember, we use the reaction quotient instead of the equilibrium constant because we're not at equilibrium, right? We're under non-standard conditions, which means that the concentration of the products and reactants are changing, and thus we need to use Q. And this is the Nernst equation, and it's going to be very important. So this step-by-step derivation is probably not as important, but see if you can follow it yourself to make sure that this equation makes sense to you.
And of course, Slum B getting down, and we got my man Christ getting down, and we got Common Sense getting down, and we got ND getting down.